All right, so let's get to equivalence relations now. So an equivalence relation is just a relation that satisfies some properties that make it. These properties are trying to capture what any notion of equality should have without being equality. So we want things to be not equal but equivalent, and the equivalence should behave well. So so let me say what they are. We'll go and revisit the previous relations from the previous video and see if they are equivalence relations. And then we will do a couple examples. So again, an equivalence relation is a relation. So that is, it's a subset of S cross S. And we're going to use the more standard notation tilde here to indicate two elements are related. Although tilde is kind of symmetric somewhat. It's like, if you rotate 180 degrees, it's the same thing. This is not a symmetric thing what we're defining. So a relation is not in general symmetric. Namely, it's not that if x is related to y, then y is related to x. So you have to actually usually check that, and that's going to be one of our conditions. So I just want to observe before I write things down that this is, although it doesn't look directed, this is actually directed from left to right. All right. So our relation, which we refer to as tilde, is called an equivalence relation if tilde is reflexive. So where does this property come from? Well, we would very much like that elements are related to themselves. If this is going to be sort of a notion of sameness, equals should be the highest notion of sameness. So an element should be related to itself. So tilde is reflexive if for all A and S, A is related to A. Great, that's reflexivity. Tilde should be symmetric because, sameness should be a symmetric notion. That is, the relation is symmetric if for all A, B, and S, A is related to B implies B is related to A. And then lastly, it should be transitive. So if we have two elements that are the same, for whatever the same means, and we have that one of those elements is the same as a third element, then all three of them should be the same. So if for all A, B, C, and S, A is related to B and B is related to C, then A should be related to C. All right, so so this is the three properties that you have to check. So note you have to check all three to be an equivalence relation. You can't just check one or two of them. You have to check all three. All right, so we're going to go back and look at the examples we just did, and then go on from there. So let's scroll up for a second here. Let's start with equals. Equals had better be an equivalence relation. If equals is not an equivalence relation, we have not captured what it means for two things. We have not captured what it means to have a notion of sameness. So, is every element equal to itself? Yes, reflexive. Great. Is equals symmetric? That is, if A and B are the same, is B and A are the same? Well, yeah, they're equal, so yes, it's just the same element. If A equals B and B equals C, is it true that A equals C? Well, yes. Equality is transitive. Great. So equals is an equivalence relation. It's the most uninteresting equivalence relation because it's equals, but nevertheless it is one. All right, now let's analyze this relation less than or equal to. Is an integer less than or equal to itself? Yes, so it's reflexive. Is it symmetric? No, it's not symmetric. It's not symmetric because 1 is less than or equal to 2, but 2 is not less than or equal to 1. So not symmetric. Is it transitive? Yes, it is transitive. A less than or equal to B and B less than or equal to C, then A less than or equal to C. Transitive. Great. So this one fails to be symmetric. Bummer, but that's okay. This is to be expected. Not everything is going to be a good notion of sameness. Let's look at this guy. Let's put it on the left this side. Is this a uh, reflexive relation? Well, no. None of the elements are related to themselves. So A related to A is never true. So not reflexive. There's no edge joining a vertex to itself. Well, I guess I shouldn't say never true. Let me strike that out. Is not true for simple graphs, which is what I have meant when I've written down a graph. So, but nevertheless, in this picture, this guy is not, none of the vertices are related to themselves. And so, so this is not in general a reflexive relation. If we were to sort of put in edges between vertices and themselves, it would become one. But as it's written here, it is not reflexive. Is it symmetric? Yes, it is symmetric. Because if A is joined by B, that by an edge, then well, the edge goes the other way too, right? It's just an edge, so B is related to A. So this is symmetric for these undirected graphs. Is it transitive? No, it's not transitive. And you can see that in this picture. Well, I say not transitive. What I mean is not in general transitive. Because 1 is related to 2 because they're connected by an edge. 2 is related to 3 because they're connected by an edge. But 1 is not related to 3 because they're not connected by an edge. Sorry, that 3 got away from me. So this guy is only one of the 3 properties. And in fact, if you sit here and you work with it and you think about the math you've experienced here at Cal State San Bernardino, I am 100% confident that all of you could come up with relations that satisfy any number of those properties and not the other ones. That means you could come up with relations that are reflexive and symmetric but not transitive. You can come up with relations that are only reflexive and so on. So there's examples satisfying any of the 3 but not the other ones. So this means that you actually have to check all of the 3, as I pointed out down here. You can't just check 1 or 2 of them. We have to check all 3. We need all 3 because there are relations that satisfy some of them, but not all of them.